Welcome, Sarah. Take it on.
Yeah, thanks very much for the introduction, and thanks everyone for coming and virtually listening to my talk today. So today I'm going to speak about some past work, some ongoing work, some future work, kind of all in this direction or dimension of trying to better understand permafrost surface water feedbacks, but particularly using some new and upcoming satellite technologies. So understanding feedbacks between permafrost and surface water is vital for a wide range of reasons, but I mean, a big one is just better constraining current and future changes in surface water and how this particularly impacts carbon emissions and ecosystems. So there's been a lot of work on kind of long-term or decadal scale changes in surface water, so changes in lakes and wetlands in the Arctic, and how permafrost thaw may be influencing those patterns. And there's been work that's found a pretty wide range of trends. So some work suggesting that we see a net drying, other work suggesting that in some places lakes are actually growing as permafrost thaws. So lots of different, it's a really active area of research, lots of patterns out there. However, a lot less work has focused on seasonal variability in its relationship to permafrost. There's been tons of work on this like long time scale, like what's happening over the past 20, 30, 40 years, less work on how lakes are changing seasonally. And the Arctic is an incredibly, I mean, seasonality is fundamental, right, to the Arctic. It's maybe we could say the most seasonal place on Earth. And a lot of the lakes in the Arctic are quite seasonally variable. And so trying to understand how permafrost might be influencing those kind of sub-seasonal patterns is a central question I've been working on for the past several years. And I have a couple of hypotheses that I'm like slowly trying to test, or that I've been working on testing. So first, the idea that lakes located in permafrost terrain are less seasonally dynamic than in non-permafrost terrain, that basically one of the roles of permafrost would be isolating lakes from the surrounding, or from basically the groundwater system, and therefore you might get a less seasonally dynamic environment, though there's many factors that could influence this. And then another hypothesis is that in permafrost terrain, we would see water levels. So if you look at just like the average water level of different water bodies, that we'd see greater spatial variability than in non-permafrost terrain for similar reasons, that essentially the less connected lakes are to each other, whether that's surface connections or groundwater connections, the more likely there is to be this kind of spatial heterogeneity in water level. And so testing these hypotheses could potentially allow us to provide greater insight into how permafrost influences seasonality, but also the other way around, if we can better understand kind of the overall patterns of surface water variability in these regions, maybe that could tell us something about what's happening to the permafrost. So those are kind of the hypotheses and ideas I've been trying to pursue. In particular, I've been going after several research questions. The first is just a basic one, which is how seasonally variable are Arctic water bodies? What drives that seasonal variability? And with permafrost being, one factor that could be driving it, but of course there are many other factors that may be influencing seasonal variability. How does permafrost influence spatial variability in water level and storage? And also, how does permafrost influence temporal variability? So these are questions that I've been thinking about over really the past 5 years or so. So what I'm going to talk about today is 3 different satellite technologies that we are currently or shortly will be using to better understand seasonal variability in Arctic surface water and its relationship to permafrost. I'm going to spend a lot of time talking about CubeSats because that's been the bulk of my work, and then much less time on ISAT-2 and SWAT, but I do want to talk about them briefly since there's exciting work happening there as well. So to start, CubeSats. Well, probably many of you are familiar with CubeSats these days. I've been working with CubeSats since about 2017, yeah, so like 6 years now since I first started working with CubeSat data. And when I started working with the data, it was very new and no one had ever heard of it, and it wasn't very well tested, but now I think it's a little more established, which has been really exciting. But basically what these are, they're small satellites, like literally the size of a little bigger than a loaf of bread. They're quite small. And companies like Planet have launched hundreds upon hundreds of these over the past 5 years or so. And as a result, they now provide daily imagery at 3 to 5 meter resolution. So as an example, you can see on the left, this is just like a random area. I actually believe this is in Siberia, but And it just shows kind of the fluctuations that you can observe at this really fine scale resolution with Planet. And this is having that 3 to 5 meter spatial resolution at near daily timescales is really a transformative improvement over what we had previously, like with Landsat, for example, in terms of like the spatial resolution. And the data has been available. They started launching the satellites back in like 2013, but there's really only good data back to 2017. And I say good data loosely because the data gets better each year. So like 2022 data is going to be better than 2017 data, but it's usable roughly going back to about 2017. And overall, we've done a lot of, I've done a lot of work with Planet, many others have as well. And in general, the conclusion is just this really high resolution can provide unprecedented insight into highly dynamic surface processes where you really want the daily data and you really want the high spatial resolution. So Planet, yes, represents this like potentially transformative advance, but there are some key challenges that make working data perhaps difficult than with other data sets. So first is the lack of an automated cloud mask. Now, this is mostly resolved now, I want to point out, but when I started working with Planet data, there was no cloud mask product or cloud mask algorithm. So you were sort of just like handed the data and you had to figure out what to do if it was cloudy without much support in doing so. Now they do produce a cloud mask product. We're working on evaluating the accuracy of that. I know others have worked on that too. It's not as accurate as some cloud masks that you might get from other more established sensors like Landsat or MODIS, but it works. Another challenge with CubeSat data has been atmospheric correction. So for a while, they did not provide atmospheric correction than they initially did, and there were some questions about its accuracy. Again, more recent data is atmospherically corrected, or there is an atmospherically corrected product available. Similarly, there's been some cool research that shows that the accuracy of that correction is not as good as, again, what you might get from Landsat, but it is available if that's something that you need. There are also a lot of issues with Planet data with basically radiometric calibration and cross-sensor calibration issues, where basically you have data coming from hundreds of different sensors, right? And these sensors are small and relatively cheap. And so small differences in how those sensors are calibrated can lead to errors in terms of like, if you're trying to measure reflectance change, it can be quite significant, those errors, depending on just the individual calibration of the satellites, because it's not data coming from one satellite, it's coming from hundreds. There also are some notable issues with geolocation errors. That's what this figure shows. It's still pretty common to find, a 10 meter or so offset in Planet imagery. It's just the geolocation is not perfect. And that's hard. It's high res data. So trying to get it really well geolocated is a challenge. And then lastly, I'm going to touch on this a bit more, but I think the biggest challenge with CubeSat data is simply the data volumes, that 3 meter data daily really quickly spirals into pretty enormous data volumes. So that's really the biggest challenge at the moment of working with CubeSat data. So back when I was a very fresh-faced PhD student, I got excited about working with CubeSat imagery and wanted to kind of see if it had some scientific value. So I posed this question of, can we observe subseasonal changes in lake area using CubeSat imagery? And so I did some work. This was back on really preliminary Planet data, actually Planet data from 2016, which today I would probably call non-usable, but at the time that was the data that existed. And so we did some preliminary work where I looked at, classified, these are different lakes in the Yukon Flats in Alaska, and classified their water in Planet imagery and produced a time series of lake area and did some other kind of interesting analyses around connectivity. And basically what we found is that, yeah, okay, if we're just interested in observing changes in lake area using CubeSat imagery, you can do it. But this first analysis that I did required a ton of manual effort. I was like individually classifying images. I was manually cloud masking because there was really no cloud mask protocol in place. And so I realized that wasn't the question. It's not, can we do this? It's, can we automate this and can we apply it over large areas, right? That's really the interesting question in terms of scientific value, is how can we take this data set that at the time, especially in 2016, was really sparse and messy, and can we, develop automated workflows that allow us to apply it over large areas. So we chose to focus on 4 study areas in Northern Canada and in Alaska. These were co-located with NASA's Arctic Burrow Vulnerability Experiment campaign, which I imagine many of you are familiar with the above campaign. So we chose these 4 study areas because they contain a range of different kind of physiographic landscapes. So you have like the Yukon Flats, which is very much a wetland environment, Mackenzie River Valley, which is a large Arctic delta, the Canadian Shield, which is a very different type of environment that doesn't have like any big rivers. It's just this very kind of like bedrocky, hummocky terrain. And then you have the peatland, lowland terrain of the Hudson Bay lowland. And all of these areas contain a range of permafrost presence within them. So that was also important for our study. And we asked the question, how seasonally variable are northern lakes across different physiographic and climatic terrains? And so to do this, we developed a method which basically tracks changes in lake area using CubeSat imagery. That's the overall approach of the method. I'm going to talk about 3 key advances that I think made this method work, given kind of some of the challenges of the data set. But in general, we applied this method over 2 types of planet imagery, Rapid Eye and PlanetScope, between May 1st and October 1st of 2017, which for our 4 study areas was exactly 75,999 images, or about 25 terabytes of data. So a pretty big data set to be analyzing. And the 3 key approaches that we use to make this analysis work and be able to apply efficiently at this scale. The first was something called basically adaptive thresholding, which is a way of classifying imagery that is based on the image itself and doesn't rely on any hard thresholds. So essentially how this works is we have this a priori guess of where the lakes are, or a priori kind of knowledge of where the lakes are. And I'm going to talk more about that step later on. But we have this knowledge of where lakes are. Then we essentially calculate the histogram. So we're looking at NDWI imagery. So NDWI is the normalized difference water index. And it's the ratio between the green and the NIR band. And it basically shows water very well. So we're looking at an NDWI image. We create the histogram of essentially like the lake pixels and the surrounding land pixels. So we know that we're getting both like water and land pixels. And then we calculate thresholds of the land threshold and the water threshold with some kind of mixed pixels in between. We calculate those thresholds based on the shape of the histogram. So even if you have imagery that's like, for one, this imagery was not atmospherically corrected back at the time, but also if you have issues with radiometric calibration problems and other things, because each classification is specific to each image, that it's robust against those kinds of errors. So we apply that classification, and then we get a nice water fraction map that you see on the right. So it's a non-binary water classification that this results in. So that's the first key step, the adaptive histogram-based classification. The second key step is object-based lake tracking. So one of the, as I mentioned, a key challenge with planet imagery that very much still exists to this day is that you often get these offsets, right, where you have geolocation error of like 5 to 10 meters. And that might not sound like a lot, but if you're trying to track fine scale changes in lake area and you're trying to look at like a single pixel over time, but that pixel is moving slightly because of geolocation error, that can definitely propagate, right? That error could propagate into your analysis. So instead of doing a pixel-based tracking approach, we use an object-based tracking approach where basically we count each or define individual water bodies and then track the amount of area within the water bodies. So we're looking at water body observations, not individual pixel observations. And so this is robust against geolocation error. It's also a pretty efficient way of doing change detection at large scales. And so when we run it over our whole data set, we get kind of the messy time series that you see on the right here of day of year versus the lake area. A little messy, but that's kind of what comes out of this initial tracking approach. And then the final step, and maybe the most important step, is figuring out how to remove cloudy and poor quality observations to go from the really messy time series you see on the left to the nice time series you see on the right that more accurately represents what's actually happening on the ground. And so the reason the time series on the left is so messy partially has to do with cloud cover, because there was no, this method relied on no cloud filtering whatsoever. So it was just like we take cloudy imagery and analyze it and then see what happens, because there was no cloud mask at the time. And there's also sometimes if the shape of that histogram is not this nice like bimodal water land histogram for whatever reason, the classification would fail. So you get these like kind of noisy data set, this noisy time series. And so we built a machine learning algorithm that basically relies on a bunch of predictor variables, including kind of like where we are in the season and the relationship between each observation and the previous and following observations. Also some information about the image itself that the observation came from. We built a machine learning model that basically allows us to pick out the high quality observations out of that time, the messy time series, and produce an overall time series of change in water area. So that's the general overall approach that we developed. Here's an example of what this looks like. This is the Yukon Flats, and you can see this area is kind of interesting because it actually has like it peaks twice in the season. Most areas don't do this, but you get kind of 2 seasonal peaks in water area. But we're able to see fluctuations in a lot of detail with this approach and pretty accurately. I don't have a slide showing this here, but we did also compare this with ground data we had collected and find generally quite good agreement as well. And then just some notes about this method for the purposes of this group. This is kind of a methods interested seminar. First, so this method, when I first wrote it, it was originally implemented in MATLAB and run on a 100 terabyte cloud server. So it's too big to run locally with that amount of data, but I had basically a cloud-based server that I could use to run this algorithm on. Since then, especially actually during kind of the pandemic time when I had less computing resources than working from home, I moved the method into Google Earth Engine. So now it runs in Earth Engine, and then one of my PhD students has also moved it into Google Cloud Platform, so it runs in a Python environment in Google Cloud Platform as well. So now there's we have different options on how you might want to run this. And in general, which I'm going to touch on a bit more, but the major obstacle to this method has been and continues to be the data volumes and just accessing the planet data, storing it, figuring out how to put the data into Earth Engine or store it in a Google Cloud bucket. All these, that's the real challenge with the method, and was at the time and continues to be, is simply just like the data access limitations. So in terms of our results, when we ran this method over our 4 study areas, we produced a seasonal time series of lake area for 85,358 lakes. So each dot you see here is an individual lake that we observe, and then each of those dots has a corresponding time series. And so what we find on average is that lakes receive a valid cloud-free observation about once every 5 days. This number, actually, we're doing some analysis currently to see if this number is changing, and it appears to not be changing. So it's very cloudy in the Arctic, and also sometimes the imagery is low quality. And so generally, even though planet data is daily, we find that about the best we can do, with some exception, is once every 5 days, which again is still really fantastic. That's a lot better than what you're going to get with other sensors, but it's not quite like data every single day. But in total from this project, it was about 2.2 million individual observations of lake area. And overall, we found a broad scale synchronous decline in lake area between May and October. That makes sense, right? In these regions, generally precipitation minus evaporation, or P minus E, is negative in the summer. So lakes are losing water, and our results kind of show that. One thing that we were surprised by, though, so here the y-axis is change in water fraction. So you can basically think of that as like the percent of the total landscape that is losing water over the summer. And what we were surprised by was not that these areas lost water, but kind of where lost the most water. And what we found is that the Canadian Shield transect was actually the most dynamic in terms of water fraction of any of our study regions, which we weren't expecting, because it's a pretty like more upland terrain, doesn't have the same kind of like river networks and channel connections that the other areas have. And we can look at this spatially. So here is showing the dynamism, which is basically the total variability in water level for each of our study regions. And unsurprisingly, in the Yukon Flats and Mackenzie River Valley, the greatest dynamism follows the river channels, which makes sense. But we were surprised by how much dynamism there was in the Canadian Shield transect, given that there aren't major river channels there. And I won't go into how we did this analysis, but basically we found that particularly in the Canadian Shield, most of the dynamism that we observe is caused by very small lake shoreline changes. So changes of less than 10 meters, like little fluctuations occurring on along the lake margin, which would be essentially unobservable by previous or other satellites, right? Because you need that like 3-meter resolution to be able to see that kind of change. And so these results have some important implications, particularly for thinking about trace gas emissions from northern waters, right? Where that seasonal inundation can really affect estimates of trace gas emissions. So, however, I should say we started this work really wanting to see what the role of permafrost was. And in that particular study, we were unable to identify a strong role of permafrost in controlling seasonal variability. There was perhaps a minor role of permafrost, but it didn't stand out super strongly amongst kind of some of the other patterns we were observing, and we didn't investigate it in more detail. However, more recently have gotten funding to expand this analysis to actually, in better detail, go after these questions around permafrost and surface water variability. And by expanding it over multiple years and over larger areas, hopefully we'll be able to go after that in more detail. And so as we've continued to work on this project, one of the things we've found, and this was a problem from the beginning and continues to be a major challenge, is simply identifying where the lakes are at high resolution. It's like a really big challenge for our work. And that might sound kind of basic, that like, okay, you just want to know where the lakes are, but really surprisingly, there have not been many high resolution, like I'm not talking like 10 meters or better resolution, water masks at global Panarctic, like those just don't really exist. What I've shown here is like the best global one, which is hydro lakes. And it's okay, like you can look at it and maybe depending on the scale you're interested in, take your interpretation, but it's missing a lot of small lakes. And if we were to zoom in further, you would see that like it's great at a global scale, but for any sort of localized or high resolution analysis, yes, not going to be accurate enough. And all these methods of looking at seasonal variability require having some knowledge of where the lakes are. That's really important, and particularly being able to distinguish lakes from rivers and other factors. So this is a really, really key step that has proven to be very challenging for this kind of approaches. And so I've been partnering with some colleagues at Woodwell, led by Andrew Mullen, who did some really exciting work recently developing a deep learning model for high resolution water mapping. Basically taking planet data, so this same data I've been working with, but we were basically, our original first guess method was just doing a simple MDWI classification and then manually checking it to make sure it looked good and fixing it if it didn't. But this is building a more robust workflow that can look at even smaller water bodies and hopefully do so in a more automated fashion. So they've built this training pipeline. It incorporates, a bunch of training data as well as planet imagery. It uses slope from DEMs and basically a convolutional neural network model that can be used to create a high resolution water mask from planet. So to show kind of what this looks like, this is the hydro lakes, which again is like about the best global data set. And then now we add in the red. The red is the results that Andrew has found with planet. So much more accurate, and also you can observe way smaller lakes, which is really exciting. We're not just limited to big lakes, but with this deep learning approach from planet, we can get a lot more detail in terms of this kind of static water mask. So this is definitely exciting work. The paper was recently accepted, so keep an eye out for it. But again, there remains this challenge, which is, this work was pretty computationally intensive, and they just performed it over 4 comparatively small study regions in Alaska. And so if we really want to perform this analysis at large regional or Panarctic scales, which again is what I'm interested in terms of thinking about like broader scale patterns in permafrost and surface water, there are still pretty significant issues with both large data volumes, as well as the challenges of accessing, downloading, and storing planet data, which is, commercial imagery. So it's not like freely available from platforms. You have to actually download it yourself. So to address these issues, we adapted this deep learning model. So we took Andrew's model, and then my group adapted it to run on Sentinel-2 imagery as well. And the reason, this was led by my PhD student, Eric Levinson, and the reason we choose Sentinel-2 imagery is because it's freely available, which is nice because Planet is not. It has a 10-meter resolution with a 5-day revisit time, so not as good as Planet, but better than Landsat, better than a lot of the other options. And it's also natively available on, say, Google Earth Engine or in Google Cloud. So there's huge advantages in terms of like ease of access for Sentinel-2 imagery. Interestingly, as a bit of an aside, we did on another project, we did a bunch of field work this past summer where to actually directly compare the accuracy of these different sensors, so of Sentinel-2 and Planet. And so we went out and surveyed a bunch of lakes in Alaska and some rivers, which is actually the figure here shows a river, but and we surveyed them with GNSS roving equipment. You can see my students Eric and Ian with equipment our equipment in that photo there, and basically found that if you, do the GNSS surveys and then classify both Sentinel-2 and Planet data and compare the accuracy, that Sentinel-2 was really not that much less accurate than Planet, which is kind of interesting. We found that Planet on average has about a 5-meter error in comparison with the ground data, where Sentinel-2 had on average a 6-meter error. So basically Planet performs worse than its stated accuracy of like 3 meters, and Sentinel-2 performs better than its stated accuracy of like 10 meters. So the difference between them is maybe not as, it's something, but it's not as significant as you might think. So this work should be published soon as well, but kind of has definitely made me think about, the value of Sentinel-2, especially given the ease of access, especially if it's not that much less accurate than Planet. So nowadays, what we're working on is fusing the deep learning model that I just discussed with the adaptive thresholding approach that I discussed a little bit previously. Basically, the deep learning model provides us with the initial guess of where lakes are, and then we can basically very efficiently run the adaptive thresholding model on that kind of initial guess, and that allows us to track lake variability over the past 7 years using Sentinel-2 imagery. So these show some preliminary results. And they're, nice, pretty figures. You can look at different aspects of open water occurrence. We've nearly finished running this over all of Alaska and are continuing that processing now. Some preliminary findings, again, this work is very much in early stages, but for example, this is looking at 2 different lakes, a lake that's connected to the fluvial network and a lake that's disconnected to the fluvial network. And basically, unsurprisingly, the connected lake is much more variable. And that kind of is a big challenge with trying to identify permafrost signals. You have to control for different levels of connectivity. But we're definitely excited about when this full data set comes together, the kind of insights we'll be able to mine with both the 7-year record and having it across all of Alaska. So to summarize from the first part talking about CubeSats, our next steps are to complete the analysis over all of Alaska, to identify intra-annual and interannual patterns in surface water variability and intersect these with permafrost data. And then I'm going to talk about surface water elevation briefly after this, but we are definitely interested in harmonizing these results with surface water elevation measurements. In terms of some of the challenges of the CubeSat work, again, this creation of the high resolution lake mask, yes, the deep learning model works really well, but there still is some manual checking and corrections involved. And so that continues to be a major limitation, or like a major time, not a limitation, a time sink on this approach. And so if we really want to run this over the entire Pan-Arctic, we probably need it to be fully automated. And it's not, that algorithm is not quite there yet to be fully automated. So we're kind of puzzling through that. And then there's also this question about Pan-Arctic analyses with Planet imagery and how possible are they, just given the data volumes and the need to download and import into Earth Engine and various things. It's definitely possible with Sentinel-2, even if it would take a while to run. Planet, it's still kind of, it's challenging. It's a good way to put it. Okay, so that's CubeSat. That's what I wanted to focus most of the time on, but I'm going to briefly touch on 2 other smaller, or not smaller, but 2 other areas of work that I think are relevant. The first I want to talk about is ISAT-2. So CubeSat data is fantastic, or optical sensor data is fantastic for looking at surface water variability. However, it's important to note that they're only observing water area, and they provide very little information about water level and water volume. And for many applications, water level and volume are very important. And so that brings us to ISAT-2. So ISAT-2 is a laser altimeter. It launched in 2018. It measures surface height. So that includes water level, measures surface height everywhere. Water level is part of that. At very high accuracy and precision. So the accuracy is about 14 centimeters, but often can perform better than that. And it can observe water level in bodies as small as 0.01 square kilometers, but it does have a repeat time of 90 days, and it doesn't observe all water bodies, so that's kind of a major limitation. We've done some work measuring water level with ISAT-2, done it both globally, also specifically in the Arctic. And I'll just go over kind of what the key steps are briefly to this approach. So the first is you need to know where the water is. Again, as I've said, this is like the major challenge in this work. I've used 2 different data sets for this purpose: the Global Surface Water Occurrence product, which is a raster data set, as well as the Hydro Lakes product, which is a vector data set. They both have advantages and disadvantages. But if we had better input data, that would be even better, but this is kind of what we have right now in terms of a starting point for knowing where the water is at large scale, so at global or pan-Arctic scales. The next step is to intersect the land surface product, which is called ATL08 from ICESat-2, to intersect that with the water mass to produce basically estimates of water level. So you can see an example here. This is an example from Kansas, not from the Arctic, but the black line basically shows the ICESat-2 tracks, and the red dots are going to be the points that we retain because they're over water. And if you look at their elevation, water's flat, right? So we can basically measure the surface elevation of the water pretty accurately. Then there's a bunch of filtering. It's actually not even that important, but basically we do a bunch of filtering on the data to remove spurious observations. I shouldn't say it's not important. It's very important to do this, but the specifics of it are less important because you might have a bunch of different tracks on different days. So a lot of filtering involved to make sure that we're retaining accurate measurements of water level. The next step is we aggregate the data to monthly time steps, and this is because of the inconsistent temporal observations. It's easier to kind of aggregate the data to a consistent time step. And then finally, we calculate seasonal variability pretty simply as just the difference between the maximum and the minimum water level observed over our study period. So we've run this globally, but more recently I've been trying to do it more specifically focusing on the Arctic and using higher resolution data where I can. And so this shows results intersecting ICESat-2 with an Arctic lake data set to look at changes in water level and storage. So the left shows how many lakes we're observing with ICESat-2, and the right shows the seasonal water variability. What you'll notice is we see the greatest variability occurring kind of along the coast and in glaciated areas, which makes sense. I think that's pretty sensible. And then kind of the areas like the North Slope of Alaska or the northern plain of Siberia are relatively stable, which again is what we would expect. But it's a little bit of a messy data set, so there's a lot of noise in all of this. And in total, this is about 150,000 lakes that we're able to observe. So what we found generally, and this is very preliminary work, is that there appears to be some level of permafrost control where lakes in permafrost environments are less seasonally dynamic than in continuous permafrost. But again, this is beginning work on a messy data set, so there's a lot more analyses to come here to really further mine these patterns. And so in terms of the next steps for the ICESat-2 work, I just further refining this method and figuring out how to deal with the fact that the data is just a little bit messy. And then also performing statistical analyses of topographic controls on water level, because we know that, permafrost is not the only thing that would influence water level variability. Topography is an important component as well, and watersheds and other factors. In terms of the challenges with ICESat-2, a big one is that we're limited by the fact that ICESat-2 has a 90-day temporal resolution and it does not observe all lakes. So you don't get, while you get this global perspective, it's not a complete global perspective. And also ICESat-2 can be pretty difficult to work with just generally because it is not currently natively available in cloud platforms, and all of the tools that NASA has developed for ICESat-2 are really great if you want to look at a small area. But if you want to look at a large area like the world or the whole Arctic, they don't work very well. I've run into lots of issues with this, so it's a little challenging. Okay, so that's ICESat-2. Now, finally, I just want to briefly touch on SWOT, which is kind of the most exciting future direction of this work. And SWOT stands for the Surface Water Ocean Topography, or SWOT mission, which launched on December 16th of this past year, so 2022, about 3.5 months ago. And SWOT is very excitingly a new NASA mission that's specifically designed to look at water level and volume. So more specifically, it is a Ka band radar altimeter that is specifically designed to measure changes in water level and volume. So unlike all these other sensors I've talked about, this one is specifically designed to do what I want it to do, right? Which is look at changes in water level and water area. So should be very uniquely useful for this purpose. And in particular, SWOT will provide measurements of water level and area for nearly all water bodies. So basically all water bodies larger than about 250 by 250 meters. And it'll provide observations about every 11 days. So this figure here shows kind of all the lakes that SWOT's going to measure, and there's a lot of them because water bodies larger than 250 by 250 meters. SWOT's designed accuracy when they designed the sensor was to basically be able to observe water level at 10 centimeter error, which is fantastic from space if it works that way. And that's for lakes larger than 1 square kilometer. For smaller lakes, the error will be a little bit larger because with radar data processing, you have to do a bunch of spatial averaging. So the smaller the lake is, the larger the error is. But in general, this is a really significant improvement over ISAT-2, which observes maybe only like 20% or 25% of all water bodies or all small water bodies, and you're only getting data every 90 days. So it's just so much more spatially and temporally comprehensive than the comparable, results from ISAT-2. And so hopefully these spatially and temporally dense observations are going to provide new levels of insight into some surface water permafrost interactions. So kind of prior to SWAT's launch, there was a airborne version of SWAT called AirSWAT. You can see a photo of the plane here, and then me and some of my colleagues as doing fieldwork supporting AirSWAT a few years ago. And so what our preliminary work from AirSWAT has shown, basically it was like AirSWAT tested a lot of the SWAT technologies, so we got that same kind of like spatially extensive water level data that we will get from SWAT. And so we did some preliminary work in the Yukon Flats, as you can see from this study area figure here, and this is showing the AirSWAT height observations. And we found that at least in this very preliminary work in the Yukon Flats, there appears to be some level of permafrost control on spatial variability in water level. That essentially in areas where you have higher permafrost presence, the spatial variability in water level exceeds the over the nearby topographic variability. Whereas if you have less permafrost, like more close to the river in the Yukon Flats, the kind of patterns in water level tend to more closely follow the hydrologic gradient, right? Just the overall kind of topographic gradient. So definitely this was really preliminary work over a small area, but suggests that if we have SWAT data at large scales globally, that there could be some potential to identify some interesting patterns. So in terms of next steps for SWAT, well, first of all, you might be wondering, when is data going to start becoming available? Well, SWAT data should start becoming available in about October at the earliest. And I say the earliest because we don't really know when it's going to be publicly released, even though the satellite is up there flying right now. And generally, my goal and many others' goal with this work is to analyze SWAT water level fluctuations to think about spatial and temporal controls on water level, just because this data will be so much more temporally and spatially dense than anything we've had previously. In terms of challenges with SWAT, there are many. One is that it's a very experimental technology and we don't have data yet. So we really don't know if it's going to work or how well it will work. So that's a big challenge. Similarly, there are definitely concerns around what kind of processing power is going to be required to analyze this data at large scales and how the data will be hosted, how we'll interact with it. There are people working on this, but it's not like this is an issue that has been resolved because the data is not out there yet. And then finally, I think a really exciting future direction is fusing SWAT with other sensors. So like taking the high resolution CubeSat data, fusing it with SWAT to be able to get these really detailed spatiotemporal variability in water storage. That is a super exciting direction. The data volumes and like software required to deploy that at scale may or may not are not clear currently, or there's a lot of work needed to really make that happen. So I know I sped through that last bit, but just to conclude, yeah, I think this is a really exciting time in surface water remote sensing. CubeSats, ISAT-2, and SWAT all provide, these amazing new insights in surface water dynamics and around the Arctic in great detail. In terms of the challenges, the primary data challenges are data volumes being large, data access, particularly for the commercial data, and for ISAT-2, it's freely available, but actually getting your hands on it's a little tricky. And then as well as just the fact that there's a lot of different platforms needed to work with this kind of data, or that people have worked with this kind of data. So often you're interfacing across different platforms. In terms of analysis challenge, the biggest problems include just data quality and noise. These are all really big data sets that are often really noisy. And so there's a lot of like outlier removal that is really important. And just generally, I've been thinking a lot about how to try to, over a huge messy data set, how to identify like a permafrost or more specific signal is hard. So working on that, but it's definitely a challenge. And yeah, lots more to come, particularly with SWAT. I hope in like 2 years I can give a talk on this and I'll have great SWAT results to show. But yeah, definitely an exciting time. So yeah, thanks very much for listening.